welcome to this talk by Ayush, who's going to be speaking about ticketed learning and unlearning schemes. So Ayush is a postdoc researcher working with Professor Shasha Racklin at MIT. He completed his PhD from the CS department at Cornell University, where he was advised by Professor Karthik Sridharan and Professor Robert Kleinberg. His interests span stochastic optimization, reinforcement learning, and machine unlearning. Strangely, not machine learning, machine unlearning. So before his PhD, he spent a year at Google as part of the inaugural brain residency program. And before Google, he completed his undergraduate studies at IIT Kanpur, where he was awarded the President's Gold Medal. So Ayush was also the winner of the best student paper at Colt 2019, and he's been a regular at Colt and NeurIPS. So you might catch him at one of these conferences. So without further ado, I'll hand it to Ayush for his talk.
Great. Thank you, Rahul. Yeah, so please feel free to stop me whenever there's any clarification or detailed questions. So this is joint work with Badi Ghazi, Pritish Kamath, Ravi Kumar, Pasen Manurangsi, and Chiyuan Zhang during an internship at Google. So as machine learning has been evolving as a field, there are more and more applications where models are trained using data collected from people. So this could be user data or user behavior data and so on. And when people are involved and data is collected from people, it's natural to have scenarios where at some point in future, someone may realize that they don't want to share their data anymore and request their data to be deleted. And there could be various reasons for deletion, including things like users realize that their data was wrongfully collected and they don't want to share their data anymore, or users' preferences changed over time in terms of how they want to share their data, and so on. And recently, there have been a lot of new laws and mandates in European Union and US and Canada that require companies to delete data when requested. However, it is not clear what it means to delete data. The basic approach to delete data from just the database, in the sense like we don't store the data in the hard drive anymore, is easy, but that is not enough. Why is it not enough? Because the modern machine learning models are very complex. They use data in arbitrary ways. And it could have happened that the data actually seeps into the training models, and it could be recovered from the training models later on. And in a sense, the data is in some sense memorized in the training models and could be recovered. And because of this confusion on what it means to remove data and so on, there was a recent ruling in which on a request to be deleted, the law actually required the company to delete the model, as well as all future algorithms that were developed using that model. So the goal of this talk is to formalize the question of machine unlearning. In particular, we provide a theoretical framework for the machine unlearning problem. And an interesting thing about this theoretical framework is that both learning and unlearning are considered simultaneously for the problem of machine unlearning. After that, we go into the algorithms for machine unlearning for various hypothesis classes. And along the way, introduce new tools and techniques that could be of mathematical interest, independent mathematical interests. And finally, we will look at some open questions and future directions and so on. So at a high level, the overview of the talk is as follows. We are done with the introduction, and we'll quickly go into this direction of learning unlearning schemes, followed by an improvement on it called ticketed learning unlearning schemes. And then I will go into specific details of mergeable hypothesis classes and a cool related problem called count to zero, and then finally conclude. Any questions so far?
Very good. Thank you. Yeah.
Okay, great. Cool. So let me directly delve into learning unlearning schemes. So in a learning unlearning scheme, there are two stages. There's a learning stage in which there's a learn algorithm that takes data and outputs a hypothesis edge. In addition to outputting a model or a hypothesis edge, it also outputs some additional information. This is just something it stores in its memory, so that at future when some users request to delete their data, Then there's another phase with an unlearning algorithm called unlearn that takes in the stored model and the additional information in aux, the data that requested to be deleted, and outputs a new model H prime. And the goal of this unlearn algorithm is to make sure that the new model H prime is similar to a world where the learn algorithm was used on the remaining training data without the samples that requested to be deleted. Okay, so at a high level, the goal of a learning-unlearning scheme is to provide methods learn and unlearn such that when there's a request to delete data, the output of unlearn is similar to a world where we just deploy learn algorithm on the remaining training data. And during the talk, I'll formalize all of these aspects of what I mean by comparing these models and so on and so forth. But this is a high-level viewpoint of what we mean by unlearning. Go on.
So at some point, I'm sure you'll do this, but this is like it has like semblances of differential privacy, right? Like it's similar to saying like if this person, I mean, it's almost like saying you want to learn a model where presence or absence of this single individual does not change the model. Like it's already unlearned in some sense.
Yeah, so it's actually like it's a slightly stronger model than differential privacy because it's kind of like a differential privacy on demand. So you remove data when there's a request to be removed. But when there's no request for deletion or no request for removal, you don't care. You can use the data in arbitrary ways.
Okay.
Quick question. So at the unlearn point, do you also output, let's say, an aux prime, such that you can loop over online additions and deletions of data?
Yeah, so I'll come to it. So in this talk, we will just care about this two-phase process. And doing this repeatedly is like a more interesting question. Like, there are some other challenges which will become clear as we go through the talk. But for now, it's just a two-stage process.
At this point, when you're talking about delete my data, please, is one row of the data set or one data point x comma y?
Great. So, okay, let's defer these questions to when I formally define the setting. This is just a high level thing because you're asking all these great questions, which will get clarified in like 3 slides. Okay, so keep your question and I will come back to it. Okay, so this is a high level viewpoint of what we want from an learning-unlearning scheme. And as we have been discussing so far, like there are actually a lot of moving parts in this high-level setup that I just described. And these moving parts lead to various trade-offs that appear in machine learning. And some of these trade-offs are the computation, like how efficient can you do both learn and unlearn algorithms, model quality, like what kind of hypothesis do you output after learning and after unlearning, how well do they perform. Then there's unlearning guarantee, like what do you compare with? And finally, there is this direction of storage or memory needed. How much information do you need to store between the learning and unlearning stage so as to perform unlearning? And these various trade-offs have been looked at in different forms in various works. But more particularly, these prior works have focused on the first 3 trade-offs of computation, model quality, and unlearning guarantee. And the goal of this talk is to look at the 4th one, which is the storage or memory needed for unlearning. So the focus of this work is to look at the space complexity of unlearning. And we will look at this from a learning theoretic viewpoint, which I'll just formalize in the next slide.
Quick question. So, for example, if you did not care about the space, would you be able to compute in some sense one model per data that was to be deleted?
Exactly. So these trade-offs need to be looked at together. In the sense, storage is an important one, like that you need to theoretically restrict in order to rule out algorithms like have a model trained on all subsets of data and just store them. And when there's a deletion, just pick the right model and service it.
One question. So when you talk about computation, is it the computation for unlearning or it includes the model training as well?
So I would say computation of both learning and unlearning. And again, like in the example that we discussed, where you are training a model on every subset, that's neither computationally efficient nor is it memory efficient, but it's very efficient from like unlearning guarantee perspective. Okay, so
Another
there are these
question.
trade-offs that need to be looked at together. Sorry, go on.
Yeah, another question that I have probably on the previous slide. So when you say you output a hypothesis class, it is still a model, and therefore that model has an error. So just to understand your problem statement, the second model H prime that you're looking at should be on a different data set, but with the same amount of error, so to speak.
Just hold that question for one more slide.
Okay.
Right. Okay, so just to give you a sense of what's coming, so we'll focus a lot on like storage and memory needed for unlearning. But at the same time, all the schemes that I will provide will have good unlearning guarantee, model quality, and computation. Okay, so let me just like go to two more slides, and then I think we'll take another break for more clarification questions. So let me formally define this setup of learning or learning schemes. So we consider a data space where the data consists of some covariates X and a label 0 and 1. In addition to that, we consider a hypothesis class script H, which contains functions little h that map the space X to 0 and 1. And we start with a dataset S consisting of n samples, where each sample is a pair of X and Y. Given these n samples, the goal of learning algorithm is to take this data and produce a useful hypothesis. In particular, the way we expect learning algorithm to produce a useful hypothesis is to assume that it is minimizing some sensible loss function, suppose 0-1 classification loss. And in particular, we require that the learn algorithm outputs a hypothesis, which is an empirical risk minimizer, which means the goal of learning algorithm is to output a hypothesis in this class that minimizes the 0-1 classification loss on the given dataset S. In addition to outputting a hypothesis, which is an ERM, it also outputs some additional memory that we call OX, which has C bits. Now, during the unlearning stage, the unlearn algorithm gets access to the C bits that the learning algorithm has produced. And on getting some deletion request Si, where Si is a subset of S of arbitrary size, the goal of unlearning algorithm is to produce a hypothesis H prime that belongs in the ERM on the remaining data. From unlearning, we require that the output H prime that is produced by the unlearn algorithm is the same ERM that we would have required if we ran a learn algorithm on the remaining data. Finally, we say that a learning-unlearning scheme is space efficient if the number of bits in OX, the quantity C over here, is polynomial in all the problem parameters. In particular, it's polynomial in log size of hypothesis class, log size of domain, and log n. So at a high level, we consider exact unlearning, where we require the output of the unlearn algorithm to be exactly the same as output of a learn algorithm on the remaining data. We only consider one-shot unlearning, where there's one stage of learn and one stage of unlearn, and not the repeated scenario where there could be sequential unlearning requests. We only consider exact ERMs, where the output of learn and unlearn algorithms are exact ERMs of on the given data set. And finally, for the sake of this talk, we will restrict ourselves to realizable setting, where we assume that there is some hypothesis in this class that can provide the correct label for all the samples in the data set. So in particular, whatever ERMs we output over here, they have zero training loss on this data set. And our goal is to develop space-efficient learning-unlearning schemes. Okay, so now let me take another break and ask for more clarification questions.
Right. So the question that I had, maybe I could ask in a different manner here. So I was wondering whether, so one way in which you might use C is to hold all the, let's say because the hypothesis is in 0, 1, you could hold all the bits for all the subsets. But that would obviously be exponential in size. And now you want to compress that information into some small polylog set such that given any subset of S, you are able to output an exact alternative.
Exactly.
Exact alternative hypothesis.
Exactly.
Hmm.
So a trivial upper bound argument here is that you just store the training data in OX. Okay, so in that case, the size of C will scale linearly with N. And that's something we don't want. We want to not store the entire training data in this intermediate memory. Okay. And thus develops,
So
sorry, go on.
it's not obvious that this is even possible, right? Like
That's a great
because it's
question. Mhm.
SI is a subset. It's not even singleton. So
Yeah, and you want this kind of requirement for all possible subsets. So you want to say like,
right.
I want to store just the right information so that if any arbitrary subset comes to ask for removal, I can update the hypothesis. Okay, and one thing maybe I should clarify right now is just for the sake of like clarity, we assume that this hypothesis is not stored in OX. So if you want to rely on the hypothesis that was output in the learn stage, you just assume that you can store that in like C-bit. So you add like a plus log H to store one more hypothesis.
Right. But yeah, I mean, it's far from obvious whether it's even possible, specifically with the fact that you require exact.
Exactly. So let's start by looking at some example, like, and that example might be like, give us some good insights on what is possible and what is not possible. So let's start with the simplest possible example that we can think of, that are 1D thresholds. So here the domain is just integers from 1 to m, sorry, natural numbers from 1 to m. And the hypothesis class is a set of thresholds where each threshold is given by a parameter a and is 0 for all x's that are less than a and less than equal to a, and 1 for all x's that are greater than a. And we want to develop a learning-unlearning scheme for this problem. So let me start by giving a data set. So consider this data set where the blue dots denote zeros and the red dot denotes 1. So I want to develop a learning-unlearning scheme for this data set. And just to recap, these are all the components that I want. I want a learn algorithm. I want an unlearn algorithm. I need to figure out what to store in OX, and so that I can update it when given any subset of removals. Now, anyone wants to take a guess of what I can do in this example? I know it's a bit difficult on a virtual talk, but you want to try like what one can do in this example? What kind of ERM one can output, and what one would
The
like to show?
max. I mean, the
So
maximum and the second largest blue point.
right. So one proposal is to store the maximum blue point and the second to maximum blue point. In the sense, the maximum blue point is a valid ERM because it separates the data.
Right. And
And then
that
I'm
is
hoping you're storing the second to maximum because if the maximum gets deleted, you can output something else.
yeah, but SI could be those two. Like it's not a single point deletion. So yeah, you can keep whatever I store. You'll ask me to remove that, and so the
Exactly.
SI. Yeah.
So
So
this
you're sort.
particular idea of using the largest negative or the largest zero sample as the valid
Yeah.
ERM is not going to work because it requires you to store everything in the central memory.
Right.
Right. But there is a scheme for this problem, which only requires you to store log m times log n bits.
So, I mean, the medians you can keep storing, like the largest, and then the point that splits the blue points into half, then again another like 1/4 and so on.
Yeah. So in some sense, the scheme that I will provide is sort of like this. Basically, what you do is you just do binary search over the space. So, and then store the entire trace of binary search. So in this problem, you start from the centermost point of the domain and look how many errors you have and go to one direction that reduces the error and so on and so forth. And eventually the binary search converges to some solution. And you output the hypothesis along the path of binary search, which has 0 error. And in the central memory, you store the path of the binary search and the number of errors you made. So in this case, you keep track of 3 hypotheses and the number of errors that each hypothesis made. Now, if there's certain deletion requests, for example, these 3 samples wanted to be deleted, the claim is that you can just backtrack on the path of binary search and again compute the first hypothesis that now would have had 0 errors. So in this case, you can just backtrack and return the hypothesis one step above, which will have 0 errors. And the claim is this hypothesis, the new hypothesis, is exactly what you would have output if you ran binary search from scratch on the remaining data. Okay, cool. So at least in some examples, we can expect some low memory learning schemes. But is this phenomena more general? Can we get some space efficient learning schemes more generally for other hypothesis classes? And unfortunately, the answer is no. So
You
this
also
idea,
like really like leverage the fact that this was realizable, that is, there were no errors in
exactly.
this. Yeah.
That's right.
So okay.
So what we realize is you cannot get space efficient learning schemes more generally. And it's not even clear how to extend this idea of binary search to product of these thresholds, just because we do not know a proper way to implement binary search in D dimensions. And in some other cases, we can prove explicit memory lower bounds that you need to store the entire data set in order to do unlearning in the central memory model. So some examples of this include if you want to do agnostic learning, even for 1D thresholds where the data set may not be realizable, you can show that you need to store the entire data set. Or if you want to do things like point functions and so on, again, you can show that you need to store the entire data set, and the proof goes through some communication complexity lower bounds. And this is not good. Like if you are storing the entire data set, why do anything creative? Just like retrain from scratch on the remaining samples. So the key question that started this work is, how can we store information efficiently for unlearning? And this led to the key like design element of this work, which is this notion of ticketed learning schemes. So in a ticketed learning scheme, the setup is very similar to a learning scheme. There's a data set, it provides its data to a learn algorithm, which outputs a ERM. In addition to it, it outputs some extra bits. However, in addition to just storing everything in the central memory aux, the learner can actually generate some tickets, which are just some small bit strings, and push them back to each user, such that during unlearning, when some samples wanted to be deleted, they bring the tickets that were assigned to them. And the unlearn algorithm can use the information stored in central memory in addition to the information stored in tickets in order to output the new hypothesis. And again, the rest of the goal is we want the unlearn algorithm to output an ERM, which is exactly what we would have gotten if the samples that wanted to be removed were never in the training data and learn was operated on the rest of the training data. So the key change over here, each person is assigned a ticket, And when a person wants to get removed, they bring their ticket with them. So if half of the data set wants to be removed, you get n by 2 tickets. So that's a lot of information. If only a few people want to get removed, you get a few tickets. So that's lesser information. But in some sense, the amount of information you get scales with the hardness of the removal problem. Like typically deleting half of the data set is a harder problem than deleting a few samples. And the information access scales proportionally. Question?
Yeah, I had a question.
Hello?
Sorry, having some audio issues. So
I think you may be muted.
yeah, can you hear me now?
Yeah, I can hear you.
Yeah,
Perfect.
sorry about that. So I
Okay.
was just saying that I was wondering, these hypothesis classes that are realizable, do they fall into some category in some high dimension? So I understand on the in R how they look because of the example shown, but what does a realizable setting look like in high dimensions? Or uh, is it that there should be some it's realizable in the hypothesis class? Is that all it means? There exists some.
Yes. All it means is that there exists some hypothesis in the class which can assign the correct label to all data sets, all samples in the data set.
Got it.
So
Okay.
there is some hypothesis that has zero classification loss.
And capital H or script H can be of infinite size as well.
Yeah. So in this setting, if you are storing things like some hypothesis in this ox, you need to pay for log cardinality of script H.
Okay. Yeah, sorry.
Yeah. So it's like it could be large, but has to be finite because you need to store these things. So
Understood.
or you need to come up with some memory model which allows you to storing like these infinite things and count them as one block or something.
Yeah.
Okay, so let's move on. So the goal of ticketed learning and learning schemes is to come up with such way of spreading information where both the size of tickets and the size of central memory is polylogarithmic on the problem parameter. So it's logarithmic in the size of hypothesis loss, logarithmic in the size of domain, and log n. And the key question we want to understand is, does allowing for small size tickets overcome the limitations of central memory model? Like we discussed a few slides ago, that central memory model actually fails to perform beyond simple classes. So does allowing for small bits and tickets allow you to have some unlearning schemes for more broader hypothesis classes?
So I had a question.
Mm-hmm.
In the previous slide, so the size of CT can be as big as log of uh, data. So I mean, like, what is stopping me from keeping xi and yi as the ticket itself?
Oh, so that doesn't help you in any way, right? Because when you're assuming that the unlearned algorithm at least has access to the samples that want to be deleted. Okay, I should have clarified that in the beginning. But you always get the information about the samples that want to be removed. What you're
Okay,
getting
I
here
see.
is additional information beyond xi, yi,
Oh, right. Okay. Yeah.
right? And the thing is like, let's look at an example on how this additional ticket can help. And let's look at the example of 1D threshold. Again, the exact same setup we looked 3 or 4 slides ago. And the claim here is, again, like in the realizable case, you can come up with a ticketed scheme where the central memory has log m bits and the ticket has size log m plus log n. And I'll compare this to the previous result in a bit, but let's first look at what you can do in this ticketed world. So this is again the data set that we were looking at before. So what can we do in this ticketed world? So in terms of
You can
hypothesis, we can
store
output
your like left neighbor, right? Like you can just keep pointing
exactly,
to.
exactly. So in terms of returning an ERM, I can choose, let's say, the smallest point which has a label 1. So as an ERM of learn, I can output this red guy. And in terms of tickets, I can store the number of repetitions of a particular sample and a pointer to the next red label in this case. So I can just store a pointer to the next one label sample. So for example, all of these blue guys get pointed to this red person, and this red one points the pointer next red one, and so on. So every person just stores like one pointer with them. And now it's clear that if I again delete some samples, I can use these pointers to compute what would have been the smallest red point in the remaining data set, and use that to compute the output of the unlearn algorithm. Right? So this is an example where assigning tickets makes sense. In particular, there's actually a benefit of assigning tickets in terms of what kind of upper bound we were able to obtain. So in this ticketed world, we can show that you use log m bits in central memory and log m plus log n bits per ticket, whereas the prior bound that was based on binary search required us log m times log n in required us to store log m times log n bits. So we save a log n factor. But more importantly, this idea of storing pointers actually also works in the agnostic case. Again, agnostic is not the main focus of this talk, so this is just a slight diversion. But for the case of 1D thresholds, you can actually come up with a ticketed scheme for agnostic datasets that are not realizable with only a log m factor blow up in the ticket size. And again, just to compare, in the central memory model, we actually have an explicit lower bound saying that you cannot do agnostic, like unlearning for this agnostic case without storing the entire training data set. So the high level idea is that tickets help for 1D thresholds. And the immediate question is, do they help beyond 1D thresholds? Are there other hypothesis classes which also enjoy some space efficient ticketed learning or learning schemes? And our key contribution is yes. In fact, there's a class of hypothesis classes that we call mergeable hypothesis classes, which has various useful examples, such that there is a general purpose and space efficient ticketed learning or learning scheme for mergeable hypothesis classes. Furthermore, beyond this general definition, you can actually come up with these space efficient, extremely space efficient ticketed schemes for various classes on a case by case basis. And we'll look like we'll go to this result and you'll realize these tickets are actually very, very space efficient. Questions?
Yeah, Ayush, very quick question. Maybe I didn't follow it fully, but let's say you have these tickets. Can you take me through how the unlearning would happen in the example you gave?
Yeah. So let's look at threshold. Yeah, of course, no problem. Okay, so the ERM I will output is the smallest red dot. Okay. Now, in the pointer, I will store a pointer to the immediately next red dot for every sample. So this blue guy gets a pointer to this red dot because that's the immediately next red dot, and so on. Okay, now suppose some samples want to be removed, like this, this, and this. Your goal is to output the immediately, like the smallest red dot in the surviving data set, which would be this guy, right? Okay, the claim is that there must be a pointer to this guy if a red dot before it got deleted by construction. Right. So when the deleted samples bring their tickets, they bring information with them on what is the smallest surviving red dot. And that's how you can just compute the updated hypothesis.
But would this ticket has to be extendable in some sense to all use cases beyond this? Let's say there's one threshold in this particular case which separates the red and blue dots. But in other cases, let's say there's a blue dot in between, would it still work? Or?
Yeah. So now you're asking more about agnostic case, or?
Yeah.
There's a very similar scheme to this that works. It just stores to need a bit more. It just needs to store a bit more pointers.
I see. Okay.
It's very similar to this. You just store like instead of one pointer per dot, you store like log m pointers.
Okay, thanks.
Okay, so let's now go into this key definition, which is mergeable hypothesis classes. So this is a bit of a technical slide. And again, like I should say right now, if you don't understand it, it's fine. Like rest of the talk is independent of this section. Okay, so we define that a hypothesis class H is C-bit mergeable if there exist three methods associated with this class. So there's an encode method that takes in a data set and outputs a C-bit string. There's a merge method that takes two C-bit strings and combines them into another C-bit string, such that if you consider two realizable data sets S1 and S2, encode them into C-bit strings and merge the corresponding C-bit strings, the output C-bit string would be exactly the encoding on the union of the two data sets. And finally, there's a decode method that takes in a C-bit string and outputs a hypothesis in this class, such that when you decode the encoding of a dataset S, you get the ERM for this. The hypothesis returned by decode is the ERM within this class on the given dataset S. So again, this is a bit technical, but many examples, including thresholds, product of thresholds, parities, all intersection closed classes, and so on, they are mergeable hypothesis classes where this quantity C is not too big. So for example, for thresholds, this C is like log X and so on.
Quick question.
Mm-hmm.
So here, correct me if I'm wrong, but S1 and S2 are data sets, and you have some C-bit string, which is where C is order of size of S1. Log S1, sorry.
So C is the log of size of domain. So this is the domain size. In some sense, you're storing like just one element of the domain for 1D threshold.
Right. So C does not depend on the size of the data.
C does not. That's important. Like, or it does not depend polynomially on the size of the data. In these examples, it does not depend on the size of the data. It's independent.
Nice.
So for example, for 1D thresholds, you can think of encoding as just storing the smallest red dot. So now you can see that if I give you two data sets with the corresponding smallest red dots and encoding, you can merge them by taking the min of the two, and that gives you the smallest red dot in the combined data set. And
Right.
the ERM is exactly the hypothesis that is based on this smallest red dot.
Yeah, understood.
Right. Okay, so the main result is the following, that if a hypothesis class is C-bit mergeable, then there exists a ticketed learning-unlearning scheme for that hypothesis class, where in the central memory you store one hypothesis. So you pay log script h, size of script h in the central memory. And in ticket, you store C log n bits. So this immediately gives a ticketed learning-unlearning scheme for all the examples that we looked at in the previous class, previous slides.
So in some sense, the VC dimension is important because it talks about like separation, irrespective of the number of data points. It talks about sort of separation of the data classes through dimension.
Okay. So this mergeable hypothesis class seems to be a subset of VC classes, but it's not like complete in the sense not all VC bounded VC dimension hypothesis class are mergeable. Okay, so let me go into the proof of this theorem. So this is going to be a very high-level proof sketch. The idea is to use, okay, so if you're given n samples, the first point is to put them in a tree. So as an example, suppose you're given 8 data points, x1, y1 to x8, y8. So we put them in a binary tree of depth 3 over here. And for any point, the corresponding ticket that we store is based on the construction of this tree. So let's look at an example. So let's look at the point x5, y5. What should we store in the tickets corresponding to x5, y5? We look at the path from x5, y5 to the root. Then we look at the leaves that are one off the path. So here it would be all these green leaves. These green leaves corresponds to data set corresponding to whatever is in the subtree starting from this node. And in a ticket, we just store the encoding corresponding to each of these one-off path nodes. So in particular for x5, y5, we will store the encoding for just the sample S6. So this is a data set of one sample. We store the encoding of S7, 8, and we store the encoding of S1, 2, 3, 4. And the idea is like using this mergeable property, we can actually use the stored information to recover a hypothesis on the remaining data set. So for example, if S5 wants to be deleted or X5, Y5 sample want to be deleted, we can first use a merge over the corresponding encodings that were stored for remaining one-off path nodes. And the claim is that once I merge the encoding on these green nodes, they give me a encoding on the remaining data set, which can be decoded to recover the ERM on the remaining samples. And this kind of idea can actually be used if you're deleting more than one samples by properly combining what are the subsets that you want to merge over.
Question here.
Mm-hmm.
So I guess over xi, yi, there is no order that you impose at this stage.
Yeah, so you artificially impose an order. But there doesn't need to be like it. You just like need to put them in a binary tree, and you need to respect that you will always put them in the same binary tree.
Mm-hmm. And somehow is the ordering known to the algorithm?
Yeah. The algorithm ordering is no, because in like you compare to an algorithm that might have used the same binary tree somehow, right? So in order to respect the fact that you recover exactly the same ERM, you need to know the ordering.
Yes. Thanks.
Okay. So let's look at the results that we have so far. We looked at mergeable hypothesis classes, provided a ticketed scheme for mergeable hypothesis classes, where the size of ticket is C times log n. In the paper, we have extension of the result, where there's this notion called as compressions. And what we show is that if the mergeable hypothesis classes has some k compressions, you can change the ticket size from multiplicative between C and log n to an additive between k log x plus log n. However, in both of the results, there's still a dependence on log n in the ticket size. And looking back at the model, in this ticketed world, the responsibility of storing the ticket is on the user who contributed their data. And depending on the application, log n may be large. For example, instead of using this kind of algorithms for unlearning, you are using this in some downstream operating systems protocol for like maintaining data structures and so on. So log n could be large. And the key question that we wanted to ask is, can we make this ticket smaller? Can we further reduce the dependence on log n? And what we realized is that for various classes that we have looked at so far, there are case-by-case algorithms where you can actually come up with ticketed schemes where the size of the ticket is log of inverse Ackermann of n. So for those who may not know this function, so inverse Ackermann is an extremely slowly growing function. It grows slower than the log star and or the iterated logarithmic of n. As an example, the inverse Ackermann of number of atoms in this universe is less than 5. And thus, these case-by-case ticketed learning and learning schemes that we develop are extremely space efficient. They have very, very small ticket size. And the interesting point is all of these ticketed schemes in the above theorem are actually obtained using a very cute independent problem that is called count to zero, which could be of separate interest. So I'll discuss this problem next. Questions?
Yeah, I had a question if you have time. So I was wondering in this particular case, so every user brings 3 tickets, let's say, size of the tree being of depth 3, or log n if there are n users. So I was wondering whether if enough users want to be deleted, this grows very large. If,
Yes.
for example, order n users want to be deleted,
Yes.
so somehow, yeah.
Yeah. Okay, so let's look at the count to 0 problem. The problem is as follows. There's a room in which Alice is like hosting a bunch of people. And from outside her door, Bob comes in and says that everyone should leave the room. Now, the rules of the game is Bob has no idea of how many people are in the room. Bob cannot communicate with anyone to know how many people are in the room. Bob cannot look inside the room. He cannot count how many people are in the room. Alice has to assign a ticket to every person, which they hand out to Bob on their way out. And the goal of Bob is to look at the set of tickets that he receives to figure out whether everyone has left or not. And the question is, how many bits should each ticket contain? So anyone wants to take a guess on some strategy for solving this problem?
Say that, can you repeat like the last part again?
Yeah. So Alice assigns some tickets to every person, which they give to Bob on their way out. And the goal of Bob is to figure out by looking at the set of all the tickets that he received, whether everyone left or not. And the question is, how many bits should some ticket or each ticket contain in this problem?
But there is no range information available to Bob either. Like there's no estimate as well.
There's no estimate as well. Exactly. So the ticket size will hopefully grow with n. So a simple strategy here is the following. Just write the number of people n in the room on each ticket, which takes log n bits. And then on their way out, they can give this ticket to Bob, and he can look at the tickets and count how many tickets he got, whether it matches the number that was written on the ticket or not. So what we realized is actually you can solve this problem with a scheme where each ticket only has log of inverse Ackermann number of bits. And this immediately gives you a method. So having access to this result that you can actually solve this count to 0 with a very small ticket size, we can use this protocol to develop algorithms for like this case-by-case basis. As an example, if you want to look at a ticketed learning scheme for 1D thresholds, we again go back to this idea of using binary search, where we do this binary search and divide the space into various components. But the way we can use count to 0 now is to actually just like look at each of these partitions and keep track of how many mistakes are made in each partition. And the idea is the partition disappears if there are no remaining mistakes in it. So you're basically counting to 0 the number of mistakes made in every partition. And this leads to like an efficient scheme for 1D thresholds where the ticket size is log of inverse Ackermann. Okay, I'll skip over the details here because of time. Okay, so now let us look into how to actually get this scheme for count to 0, where the ticket size is log of inverse Ackermann. So this involves some very nice math. It's actually based on the idea of constructing size indexing Sperner families. Maybe I'll just do a quick introduction to this and go over the details. So a size indexing Sperner family is a set of sets. So it's a Sperner family Q is a set of sets Q1, Q2, Q3, and so on, such that no two sets in this family are subsets of each other. We say that the Sperner family is size indexing if the size of the corresponding sets grows linearly. In particular, the number of elements in set Q1 is 1, the number of elements in set Q2 is 2, and so on and so forth. And finally, we define the alphabet size for the Sperner family to be the number of distinct characters that we need in order to construct some particular sets. So an alphabet I means the number of distinct characters that we need in order to construct the family from Q1 to Qi. So at a high level, you can actually use existence of such Sperner families to come up with a count to zero scheme. The idea is very simple. So in order to solve this count to zero problem, before going into the room, Alice and Bob agree on a size indexing Sperner family. Then Alice just counts the number of people n in the room and chooses a set Qn from the corresponding size indexing Sperner family. So the number of items in this set Qn is exactly n. Then Alice opens up the set Qn, looks at the characters in the set Qn, and assigns one character to every person. So because there are n characters, each person gets one character. And as people leave the room, they return their tickets to Bob. In particular, they provide Bob with characters from this set Qn. And the claim is by looking at the set of characters that Bob has received, Bob can determine whether all the people left the room or not. In particular, all that Bob needs to do is to construct the set by collecting all the characters together and checking whether that actually belongs to the Sperner family they agreed beforehand or not. If it does, then all the people have left the room. If it does not, then some people are still remaining. And Bob can be sure that this protocol works because the family they agreed on before was a Sperner family. So it can never happen that not all people left the room, but still it became a member, the set of characters that Bob collected became a member of the Sperner family, just by the property of Sperner families. Question?
Yeah, I had a question. Does the Sperner family for size n not depend on n? Or maybe I'm missing something.
So number of characters, that's a great question. So the insight is like any Sperner family can be used to construct a ticketed scheme. And the tickets contain the characters from the set Qn. So the size of the ticket is exactly log number of alphabets that you need to construct the set Qn. And what we can show is that there exists a size indexing Sperner family where the number of alphabets that you need to construct the corresponding set Qn is inverse Ackermann of n. And this immediately gives you a count to zero scheme with this log of inverse Ackermann of n. So I hope this answers your question in the sense that, yes, the number of characters that you need grows with n, but the rate at which it grows is controlled by inverse Ackermann.
Yeah, it's so slow that it doesn't matter. So fix something.
Right. Right. So we do provide a constructive proof for this Sperner family in the paper. Okay, so this was the technical side gig, but let me just go back to all the results that we have looked at so far. So the main result of the talk was to provide a ticketed learning-unlearning scheme for mergeable hypothesis classes, where the ticket size grows as C times log n, where C is the size of the mergeable encoding. Then if the hypothesis class satisfies additional properties like it's compressible, you can improve this to an additive factor of log n. And then on a case-by-case basis, you can actually make it even smaller and go to like log of inverse Ackermann. However, all of these depend on n. So a natural question that appears is some dependence on n necessary? Or can we come up with ticketed schemes where the ticket size and central size could both be constants? And we actually provide a lower bound that shows that if your hypothesis class is non-trivial, in the sense it contains two distinct functions, then there cannot exist a ticketed scheme with both the central memory to be constant and the ticket size to be constant or independent of n. And this is shown by reducing the problem to the lower bound that argues that there does not exist a ticketed scheme for count to zero, where both the central and ticket size to be constants, which is obtained by showing that there does not exist any size indexing Sperner family, with alpha bit size to be universally upper bounded by some constant. So alpha bit has to grow within. And the takeaway is we cannot remove the dependence on n from both the central memory and the ticket size. However, it does leave open the question, can we actually remove the dependence on n from tickets while we are still willing to pay log n or like even maybe slightly more factor in the central memory? And can we even do this for like some simple classes? Okay, so let me just conclude and summarize what we have discussed so far. We consider the memory viewpoint of machine unlearning. We provided ticketed learning-unlearning schemes, which we argued is a practical model for spreading information amongst the participating agents, where users have to pay the price of storing small additional tickets on their own devices to get the benefits of unlearning. We introduced this notion of mergeable hypothesis classes and provided a general purpose ticketed learning-unlearning scheme for mergeable hypothesis classes. Finally, we also looked at some improved ticketed learning-unlearning schemes for certain classes that are obtained on a case-by-case basis by using a shared count-to-zero protocol, where the count-to-zero problem is solved by constructing of some size indexing Sperner families with small alphabet size. But we barely scratched the surface. Like, this problem is very rich. There are many directions that could be explored. And one particularly interesting direction is, can we get these ticketed schemes for general VC classes, in particular beyond mergeable hypothesis classes? And then there are some direct problems in the sense, can we extend this to only return approximate ERM where we are allowed to make a few mistakes? Can we do approximate unlearning in the sense we don't require to recover the exact model, but we are fine with some epsilon delta kind of guarantee as people use in differential privacy? Can we extend this model to multi-shot unlearning where we can have iterative additions and removals? And finally, can we do this for more practical machine learning models? So far, we have looked at these very theoretical classes, which are good to study, but maybe we want to develop some things for more practical models. Like, can we even get some space efficient schemes for linear separators, one of the simplest practical machine learning model? And finally, like, one interesting question is computation, in the sense, maybe I am fine by storing everything in the data set, but I don't want to retrain from scratch. So can I do something quicker than retraining from scratch and still obtain a good hypothesis? And that's it. Thank you. And there are a lot of like combinations of these things that can be looked at. So I feel this is a very rich area and definitely very interesting. Yep. Cool. Questions?
Yeah, thanks, Ayush, for the wonderful talk. I think you introduced us to the unlearning problem and some different perspectives on it. So I'll throw it into questions to the audience.
Yeah.
Yeah, I had a question. So maybe if no one, yeah. So my point is, what are mergeable classes like? So if I wanted a VC dimension, so I understood your 1D case, but let's say there's a VC dimension of the hypothesis class being 2. Does that mean that I can construct a mergeable class from that, or I didn't fully understand?
Interestingly, if the VC dimension is 2, then
Or
you
some
can.
number.
No, but if the VC dimension is 2, then you can.
I see. It's a special.
It's a special one. Let me check VC dimension 2. Oh no, that's for VC dimension 1. So VC dimension 1, any VC dimension 1 class is mergeable, but I don't know what VC dimension 2.
And this is irrespective of the dimension of X and so on.
Yeah. So there's this like very nice notes by Shive and David called like 2 notes on classes with VC dimension 1. So essentially, like all VC dimension 1 can be written in some tree, and you can actually do this merging on the tree. But I don't know how to do this beyond, like, the question you're asking is, are general VC classes mergeable? And I don't know.
Right. And I sort of see the point of optimizing for the ticket size.
Mhm.
But there are other objectives, as you yourself have pointed out. So have you looked at some of these future directions that you yourself mentioned? For example, in the machine learning community, some of these approximate unlearning frameworks are looked at. So is that something interesting, or have folks done something on that?
Yeah, so I've looked at approximate unlearning, but like, okay, so there are a few things, right? First of all, you can just look at approximate unlearning and forget about memory. So you can look at approximate unlearning in computation and say, I'll store the entire data set. I just want to recover an approximate good solution. And I want to do it faster than retraining from scratch. Right. So some people have looked at this direction. The kind of direction I have looked at is, okay, you want to return an approximate solution, and you do have some constraints on memory. So you don't want to store the entire training data set. Can you do something better than just using differential privacy?
Right.
And so on. And some people have also looked at, okay, like I don't care about like memory needed, but I care a lot about model quality, unlearning guarantee, and computation. In the unlearning phase, can I store like a lot of duplicates that can be used somehow to compute a new function?
Yeah, I've looked at some of those. Those are the naive solutions that one might come up with for.
Exactly.
So I was wondering if we put a bound on the number of the size of the subsets that will be deleted, is that an interesting notion? Because like if the size is one, then I can just take it and store all the classifiers without just the classifier without loading that. And
Yeah, I
that
think
will
that's a very interesting question. Like, I have some thoughts, but no concrete results.
okay.
But your intuition is correct in the sense, if you know you're always only deleting one sample, then in the ticket for that one sample, you delete the hypothesis trained on everything else.
Yeah.
Right? Now, one can imagine that if I give you like a constant number of deletions, you can argue
Yeah.
that you can compose these hypotheses in some way.
Yeah.
And the error in composition scales with the number of times you do this composition, which is somehow bounded because you're guaranteeing you're not composing too much.
Mm-hmm.
Yeah.
Also, these are like worst case deletions, right? In particular, one could imagine like only a distributional requirement, saying that the deletions are they have
Exactly.
some.
Yeah.
I mean, yeah.
Yeah, I totally agree with you. You can imagine like a distributional requirement and then hope that there are two worlds, right? Either the distribution is smooth in the sense like uh, there's some properties of the distribution that you want to rely on, or the fact that even during learning, you know what distribution of a learning request would be. So you can
Right.
prepare for the more potential unlearning requests like earlier.
Hmm. Hmm.
Yeah. And again, I feel like all of these questions that we're asking on theory are very far away from like how to do this for a neural network, which like, okay, we do not even learn know how to learn properly with the neural network. I think like trying to provably unlearn will be like an interesting question over there.
So one aspect also is, in some sense, certification. Like, I mean, this may be like a bit of a digression, but uh, the fact is that you also want to convince the like you're looking at your motivating example. That the individual needs some sort of a guarantee that this has been done. Like the hypothesis class is actually
Mhm.
one that, so it's just the transparency of the method, or is there a, I mean, I was wondering if there's a simpler way of certifying that, oh look, now I have a H prime that is far away. Yeah.
Right. So I have like three thoughts over here. So the first thought is, if your method is provably unlearning, you don't need a certificate. You can just say like, look, I use a method that provably should do the right thing. and then you can just trust that I implemented the code that I showed you.
Right.
The second one is you give me a very strong evaluator, in the sense, here is the unlearning method and here is the evaluator. And this evaluator, like, you can try it in practice and you can see that it certifies that this does well.
Hmm.
And the third is more like a case-by-case certificate, in the sense, I give you a certificate that you have been removed from the data set somehow. And the last one is like very unclear to me how to like theoretically pose the problem of certification.
Right.
Dhruva has a question from the audience. So he says, great talk. I had a question about iterative unlearning and tickets. Wouldn't one like to avoid reissuing tickets? How badly do you think this would affect the ticket size?
So to be honest, I've not thought about iterative unlearning much. And in some cases, it's actually fine. Like if you look at the threshold example, you can just keep on using the future pointers.
So I guess this question seems to be like,
But
if you were to issue tickets, you could probably solve the problem.
can you repeat?
Maybe the question points towards reissuing tickets for the iterative problem. So treat it as a fresh problem each time, and then. But I guess then you're back to the same question, right? If you are allowed to reissue tickets, then.
Right. I feel like what I described in the talk is one of the simplest setting to actually like pose a memory question over here. So I feel like extending this in any other direction could be like challenging, non-trivial, interesting.
Okay. Maybe I can stop recording the talk and then we can carry on.
Sure. Yeah.